Imagine standing on a beach 74,000 years ago. The sky, once blue, has turned an apocalyptic gray. Ash falls like snow around you. The sun, a distant memory, has been replaced by darkness that stretches across continents. The air is difficult to breathe. Plants are dying. Animals are vanishing. Yet somehow, against astronomical odds, you survive. Not just you, but enough humans to ensure our species doesn't vanish from the face of the earth. A handful of men and women who will become the ancestors of nearly every human being alive today. This isn't science fiction. This is what many researchers believe actually happened roughly 74,000 years ago when a supervolcano erupted on the island of Sumatra in present-day Indonesia. An event so catastrophic it nearly ended humanity before civilization had even begun. The Toba catastrophe theory suggests that this eruption created a global winter lasting years, perhaps decades. It reduced the human population to as few as 3,000 to 10,000 breeding pairs worldwide, a genetic bottleneck from which we nearly didn't recover. Yet despite this apocalyptic scenario being widely accepted for decades, something doesn't add up. New evidence challenges the very foundation of this theory. Archaeological discoveries contradict the expected patterns. Genetic studies reveal puzzling inconsistencies. The questions multiply. If Toba was so devastating, why do we find continuous human habitation in some regions? If humanity was reduced to a few thousand individuals, why don't our genes show clear evidence of this bottleneck? Perhaps most troublingly, if the conventional Toba catastrophe theory is wrong, what actually happened 74,000 years ago? What forces shaped human evolution during this critical period? And what does this reveal about our species' remarkable resilience? Tonight, we venture into one of anthropology's most enduring mysteries. What really happened 74,000 years ago that nearly ended humanity? We'll examine competing theories, unexpected evidence, and the profound implications for understanding our shared human story. You're about to discover that the truth may be far stranger than scientists initially believed. The story of human survival against catastrophic odds, whether volcanic winter or something else, entirely reveals something profound about our species and our place in Earth's history. The answers matter not just for understanding our past, but for navigating our future. If we survived one global catastrophe in our infancy as a species, perhaps the clues to surviving future threats lie buried in the ash of ancient Toba, in the volcanic debris across Asia, in ancient stone tools found in unexpected places, in the very DNA that flows through your veins. Evidence waits to be interpreted. Tonight we'll piece together a puzzle that spans continents and challenges our understanding of human origins. What if Toba wasn't just a disaster, but a crucible that fundamentally altered human evolution? What if the near-extinction event forced adaptations that made us uniquely human? Or what if the entire narrative we've constructed around Toba is fundamentally flawed? Our journey begins in Indonesia, where Mount Toba's ancient caldera, now filled by Lake Toba, offers silent testimony to one of Earth's most violent moments. Here, roughly 74,000 years ago, the largest eruption in the past 2.5 million years shook our planet. Toba ejected an estimated 2,800 cubic kilometers of material, enough to bury the entire state of Rhode Island under half a mile of ash. For comparison, the 1980 Mount St. Helens eruption produced just 1 cubic kilometer of material. The ash cloud would have circled the globe, blocking sunlight, triggering a volcanic winter, and devastating ecosystems worldwide. Plants withered, food chains collapsed, and our ancestors, still in the early chapters of the human story, faced extinction, or so we thought. Tonight, we'll re-examine this narrative, following the evidence where it leads us, even when it contradicts established theories. We'll explore alternative explanations and consider what they reveal about human resilience. Stay with me as we unravel this mystery. We'll examine volcanic glass found across continents, analyze ancient toolkits that shouldn't exist, and explore genetic evidence that tells a complex story of our near extinction, or perhaps our surprising continuity. The truth about what happened 74,000 years ago remains elusive, contested by scholars across disciplines. But in that uncertainty lies an invitation to discovery. Tonight, we step into that gap, searching for answers that might finally explain humanity's closest brush with oblivion. Chapter 2: The Catastrophe Hypothesis. The magnitude of what potentially occurred 74,000 years ago can hardly be overstated. If the traditional Toba catastrophe theory is correct, it represents the closest Homo sapiens has ever come to total extinction, a moment when our entire species hung by a thread. According to this theory, the Toba eruption unleashed a global winter lasting years, possibly decades. Temperatures plummeted by up to 15 degrees Celsius in some regions. Plants withered under skies darkened by ash. Food chains collapsed. Our ancestors, still hunter-gatherers with primitive technology, faced starvation. The genetic evidence, at first glance, seemed to support this narrative. Studies of mitochondrial DNA, a genetic material passed exclusively from mothers to children, revealed what appeared to be a population bottleneck around this time period. This bottleneck suggested that the entire modern human population descended from a small number of survivors, perhaps as few as 3,000 to 10,000 breeding pairs. From this limited gene pool arose the remarkable diversity we see today across continents. If true, this makes the Toba catastrophe more significant than any historical event we typically study. More consequential than the rise and fall of Rome, the Black Death, or both world wars combined. It nearly ended our species before civilization began. The stakes of this investigation could not be higher for understanding human evolution. If Toba created the bottleneck, it means environmental catastrophe, not competition with Neanderthals or other hominin species, was our greatest existential threat. It would mean our ancestors survived conditions far worse than anything in recorded history. They endured years of nuclear winter-like conditions with stone tools and fire as their only technologies. No agriculture, no permanent settlements, no written knowledge to preserve wisdom. Their survival would be nothing short of miraculous, an extraordinary testament to human adaptability and resilience. Every human alive today would owe their existence to those few thousand individuals who somehow endured the aftermath of Toba. But the implications extend beyond academic interest. Understanding how early humans survived such a catastrophe could provide vital insights for modern existential threats, from climate change to nuclear war to pandemics. Ancient wisdom embedded in our past. If a few thousand Stone Age humans could survive a decade of volcanic winter, perhaps their strategies could inform our own preparations for worst-case scenarios. Their story becomes not just history, but potentially a survival guide for civilizational resilience. Moreover, if Toba created a genetic bottleneck, it helps explain certain patterns in human genetics, including our remarkable genetic similarity compared to other primate species. Chimpanzees living in a single forest can have more genetic diversity than humans across continents. This unusual genetic uniformity has puzzled scientists. A severe bottleneck around 74,000 years ago would provide a compelling explanation. We lack diversity because we nearly went extinct, with just a small founder population surviving to repopulate the planet. The Toba catastrophe theory also potentially explains why humans display what anthropologists call behavioral modernity, the suite of complex behaviors including symbolic thought, art, and sophisticated tool use after this time period, but rarely before it. Perhaps catastrophe spurred innovation. Those who survived were likely the most adaptable, the most inventive, the most cooperative. Natural selection would have strongly favored these traits, potentially accelerating human cognitive and cultural evolution. But here's where our story takes its first dramatic turn. What if this widely accepted narrative taught in anthropology classes, featured in documentaries, cited in hundreds of scientific papers, is fundamentally wrong? Or, at least, dramatically oversimplified? Recent discoveries have begun to challenge the Toba catastrophe theory. Archaeological sites in South Africa show continuous human occupation through the supposed bottleneck period. Stone tools found in India lie both below and directly above the Toba ash layer. Genetic studies using more sophisticated methods have failed to find clear evidence of a severe bottleneck coinciding with Toba. Some populations show different patterns of genetic diversity than would be expected if a single global near-extinction event occurred. Climate modeling has suggested the cooling effect might have been less severe than initially thought. The eruption may have ejected less sulfur, a key component for atmospheric cooling, than earlier estimates suggested. If the traditional Toba catastrophe theory is wrong, we must reconsider fundamental aspects of human evolution. What actually happened during this critical period? Did different human populations experience different fates? Was there another cause for the apparent genetic bottleneck? And perhaps most intriguingly, if not Toba, what other forces shaped early human populations during this period? Competition with other hominin species? Different environmental pressures? Previously unidentified catastrophes that left fewer geological traces? These questions aren't merely academic. They go to the heart of what made us human, what tested our ancestors' resilience, and what evolutionary pressures shaped the species that would eventually build global civilization. The mystery deepens when we consider that Toba erupted during a period when multiple human species coexisted: Neanderthals in Europe, Denisovans in Asia, various populations of Homo sapiens spreading from Africa, possibly other hominin species not yet discovered. Did Toba affect these populations differently? Did some face extinction while others persisted? The puzzle grows more complex and more fascinating the more we examine it. Tonight, we'll follow the evidence wherever it leads. Chapter 3. Before the Ash. To understand what happened 74,000 years ago, we must first understand the world as it existed before Toba erupted. This was a planet already in the grip of an ice age, with vast ice sheets covering much of the northern hemisphere. Yet despite these harsh conditions, humanity was in the midst of a remarkable expansion. Homo sapiens had evolved in Africa roughly 300,000 years ago, developing the anatomical features that make us recognizably human: our rounded skulls, prominent chins, and slender builds. By 74,000 years ago, these early modern humans had begun their first migrations out of Africa. Small bands ventured across the Red Sea into the Arabian Peninsula, following coastlines rich with marine resources, gradually pushing eastward. This was not the only human expansion. Our species had previously ventured out of Africa around 120,000 years ago, reaching as far as the Levant, modern-day Israel and Syria. But those earlier populations appear to have retreated or died out. The world these humans inhabited was unimaginably different from our own. Vast herds of megafauna roamed every continent: woolly rhinos and mammoths in Eurasia, giant ground sloths in the Americas, marsupial lions in Australia. Sea levels were approximately 80 meters lower than today, exposing vast coastal plains now hidden beneath oceans. Rivers flowed through what are now undersea canyons. Islands that today separate continents were connected by land bridges. Our ancestors shared this world with other human species. Neanderthals had already occupied Europe and parts of Asia for hundreds of thousands of years, developing their own sophisticated technologies and cultural practices. They were not our ancestors, but our cousins. In the mountains and forests of Asia lived the enigmatic Denisovans, known primarily from tiny fragments of bone and teeth discovered in a single cave in Siberia. Genetic evidence suggests they were widespread across Asia. Other hominin species likely existed, the recently discovered Homo luzonensis in the Philippines, Homo floresiensis, the hobbits, on the Indonesian island of Flores. The human family tree was more like a bush with multiple branches growing simultaneously. These different human species occasionally encountered one another. We know this because genetic evidence shows interbreeding occurred. Most non-African humans today carry 1 to 4% Neanderthal DNA. Some Asian populations carry up to 6% Denisovan DNA. This was the complex human landscape when Toba's rumblings began. Multiple human species, each with their own territories, technologies, and adaptations. A world on the cusp of what would become the great human expansion across the globe. The technologies these early humans possessed were sophisticated for their time, but primitive by our standards. Stone tools were crafted with increasing precision. Fire was controlled and used for warmth, protection, and cooking. Language almost certainly existed, though its complexity remains debated. These humans possessed the same FOXP2 gene variant that enables modern speech. They likely communicated with words, gestures, and perhaps even rudimentary symbols. Art and symbolic thinking were emerging. Ochre, a natural pigment, was processed and used, potentially for body decoration or symbolic purposes. Shell beads have been found dating to this period, suggesting personal adornment and possibly trade. Social structures were complex. Humans lived in bands of perhaps 20 to 50 individuals, likely with kinship as the organizing principle. They moved seasonally, following day migrations and plant cycles. Knowledge passed orally across generations. Their understanding of the world combined practical wisdom with what we might call spiritual or supernatural beliefs. Evidence suggests ceremonial burial of the dead was practiced, implying concepts of an afterlife or reverence for ancestors. These humans were highly adaptable, capable of surviving in diverse environments from African savannas to Middle Eastern deserts. But they remained vulnerable to environmental shocks, drought, climate change, or the catastrophic event we're investigating tonight. When Mount Toba began to show signs of activity, humans in Southeast Asia would have had no concept of what a supervolcano was. They might have noted earthquakes, gas emissions, or other warning signs, but could not have comprehended the scale of the coming disaster. The human populations closest to Toba, those in India and Southeast Asia, would be the first to face its effects. Archaeological evidence suggests humans had reached these regions by this time, though in small numbers. Their fate, whether they perished entirely or somehow endured, lies at the heart of our investigation. Did the first human pioneers into Asia face extinction? Did they survive but suffer extreme population reduction? Or is the story more complex than we've assumed? The archaeological record immediately before Toba shows humans developing increasingly sophisticated technologies. Middle Stone Age toolkits included specialized implements for different tasks, scrapers for hides, points for hunting, blades for cutting. Some populations were beginning to exploit marine resources intensively, fishing, collecting shellfish, hunting coastal mammals. This dietary expansion represented a significant adaptation, providing reliable nutrition even when land resources were scarce. Early trade networks may have existed, with materials like obsidian and ochre transported over distances of hundreds of kilometers. These networks suggest social connections extending beyond immediate family groups, the beginnings of wider human societies. These achievements make what happened next all the more dramatic. Whether through Toba or other factors, human development would face its greatest test. The question that drives our investigation: how did our ancestors respond to this existential threat? As we continue our journey tonight, we'll examine the moment when Toba erupted and the conflicting evidence about what happened next. The conventional narrative of near extinction will be tested against new discoveries that suggest a more nuanced reality. Chapter 4: The Eruption's Footprint. The moment of Toba's eruption must have been apocalyptic for anyone within hundreds of kilometers. The ground would have shaken with unprecedented force. the sky would have darkened to midnight at noon. Thunder would have rolled continuously as the ash cloud surged upward. Modern volcanologists estimate the eruption lasted approximately 2 weeks of continuous explosive activity. The volcano ejected approximately 2,800 cubic kilometers of magma, enough to cover all of Manhattan Island to a depth of 6.5 kilometers. For comparison, the 1980 eruption of Mount St. Helens ejected about 1 cubic kilometer of material. The 1815 eruption of Toba, which caused the infamous year without a summer, ejected about 160 cubic kilometers. Toba dwarfed them both. The eruption was so massive it created a caldera, a volcanic depression formed by collapse, approximately 100 kilometers long and 30 kilometers wide. This massive crater eventually filled with water, forming what we now call Lake Toba in Sumatra. The most compelling evidence for Toba's global impact comes from a distinctive layer of volcanic ash found across much of South Asia. This ash layer, approximately 15 centimeters thick in India, can be definitively linked to Toba through chemical analysis. Volcanic glass shards matching Toba's chemical signature have been found as far away as East Africa and the South China Sea. This ash, carried by atmospheric circulation, would have blocked sunlight, lowered global temperatures, and contaminated water sources. The climatic effects would have been severe. Computer models suggest global temperatures may have dropped by -5 degrees Celsius on average, with much greater cooling in continental interiors. Growing seasons would have shortened or disappeared entirely in many regions. These temperature drops would have triggered ecological cascades. Plants would have died from cold and lack of sunlight. Herbivores would have starved without plant food. Predators would have followed. Entire food webs would have collapsed in the most affected regions. For humans, the immediate impacts would have included respiratory problems from ash, contaminated water supplies, wildfires ignited by hot volcanic material, and the psychologically devastating experience of darkness at noon. A world suddenly unfamiliar and threatening. But the longer-term impacts would have proven even more challenging. Food scarcity would have stretched for years as ecosystems slowly recovered. Migration routes would have been disrupted. Traditional knowledge about resource availability might suddenly become useless. This is where the traditional Toba catastrophe theory makes its boldest claim, that these conditions were so severe they reduced the global human population to just a few thousand breeding individuals, creating a genetic bottleneck from which all modern humans descend. The first evidence supporting this theory emerged in the 1990s from genetic studies. Researchers analyzing mitochondrial DNA passed exclusively from mother to child found patterns suggesting a population bottleneck roughly coinciding with Toba's eruption. These genetic studies appeared to show that modern non-African humans descended from a small founder population that expanded rapidly after around 70,000 years ago, consistent with recovery following a catastrophic population crash. The timing aligned remarkably well with Toba, leading to the widely accepted theory that the supervolcano had nearly exterminated our species just as we were beginning our global expansion. It was a compelling narrative of near extinction and remarkable recovery. Further support came from climate modeling. Scientists used sophisticated computer simulations to estimate Toba's climatic impact, concluding it could have caused a volcanic winter lasting 6 to 10 years, with some effects persisting for decades. Archaeological evidence also seemed to fit the pattern. Human sites appeared scarce during this period, with apparent gaps in occupation that could represent population crashes. Stone tool technologies showed disruptions in their developmental sequences. The theory gained such widespread acceptance that it became the standard explanation for human population patterns during this period. Textbooks, documentaries, and scientific papers cited the Toba catastrophe as a defining event in human evolution. But science advances through questioning established theories, and over the past decade, Researchers have uncovered evidence that complicates and potentially contradicts the traditional Toba catastrophe narrative. This is where our mystery deepens. The first cracks in the theory appeared at Jewelapuram in southern India. Here, archaeologists found stone tools both below and immediately above the Toba ash layer, suggesting continuous human presence, despite being relatively close to the eruption. These weren't crude implements suggesting desperate survival, but sophisticated tools showing technological continuity. The people making these tools appeared to have carried on their cultural traditions despite living through one of history's most powerful eruptions. Similar evidence emerged from South Africa, where excavations at sites like Pinnacle Point revealed continuous human occupation through the Toba time period. No evidence of population collapse, technological regression, or cultural disruption appeared in the archaeological record. Marine core samples from Lake Malawi in East Africa failed to show the temperature drop that would be expected if Toba had triggered a prolonged global winter. The local climate appeared remarkably stable through the period of the eruption. Even the genetic evidence came under scrutiny. New analytical methods and larger sample sizes suggested the apparent bottleneck might reflect sampling bias or statistical artifacts rather than actual population reduction. Or it might have occurred at a different time. Some researchers began to suggest the bottleneck might have happened earlier, perhaps 150,000 years ago, and for different reasons, such as an extended drought in Africa. Others questioned whether a severe bottleneck occurred at all. Studies of artifacts from this period raise further questions. If humanity was reduced to a few thousand individuals centered in Africa, why do we find evidence of sophisticated technologies developing independently on different continents during this period? The plot thickened further when researchers discovered that different human populations showed different genetic patterns during this time frame. Some show signs of expansion, others contraction, others stability, not the universal bottleneck the theory predicted. These discoveries have forced scientists to reconsider what actually happened 74,000 years ago. If Toba didn't nearly exterminate humanity, what explains the genetic patterns we observe? If some populations survived relatively unscathed, why did others apparently decline? Could Toba's impacts have been regionally variable, devastating in some areas but manageable in others? Could different human populations, with different technologies and cultural adaptations, have experienced drastically different outcomes from the same environmental shock? Or is it possible that Toba's role has been fundamentally misunderstood? Perhaps the eruption was less climatically impactful than believed. Maybe other factors, competition between human species, climate shifts, or diseases, played more significant roles in population changes. As we pause here at the end of our first act, the mystery of what happened 74,000 years ago has only deepened. The conventional narrative of Toba's near extermination of humanity appears increasingly questionable. But if not that, then what? In our next segment, we'll explore the alternative theories that have emerged to explain this critical period in human evolution. We'll examine new genetic evidence that tells a more complex story of human populations during this time. We'll investigate whether different human species, Neanderthals, Denisovans, and various populations of Homo sapiens experienced Toba's effects differently. And we'll consider whether multiple factors, rather than a single catastrophe, shaped human evolution during this period. The stakes of this investigation remain immense. Understanding what really happened 74,000 years ago isn't merely academic curiosity. It's about understanding the forces that shaped human evolution at a critical juncture, nearly erasing our species before civilization began. Stay with us as we venture deeper into one of anthropology's greatest mysteries and potentially rewrite the story of humanity's closest brush with extinction. The answers may surprise you, challenge conventional wisdom, and reveal new insights about human resilience. Chapter 5: Contradictions in the Ash. As we venture deeper into our investigation, the conventional Toba catastrophe theory faces mounting challenges. If a supervolcano caused a 6 to 10 year volcanic winter that nearly exterminated humanity, we should find clear evidence in the archaeological record, evidence that increasingly appears to be missing. Let's begin with one of the most striking contradictions: stone tools found at Jewelapuram in southern India. These sophisticated implements appear both below and directly above the Toba ash layer, with no significant gap in occupation and no technological regression. The tools above the ash display the same craftsmanship as those below. No desperate adaptation to catastrophic conditions. No technological simplification that would suggest a population under extreme stress. Just continuity, as if life carried on despite the eruption. This is perplexing because southern India lies relatively close to Toba. Models suggest this region should have experienced some of the most severe effects. Yet the archaeological evidence suggests humans there weathered the eruption without dramatic disruption to their way of life. Similar contradictions appear in South Africa, particularly at sites like Pinnacle Point and Sibutu Cave. Here, archaeologists have found continuous human occupation through the Toba timeframe, with no evidence of population crash or cultural disruption. These sites show sophisticated technologies developing steadily through the period when humans were supposedly fighting for survival. Stone tools become more refined, not more primitive. Hunting strategies grow more complex. Symbolic behaviors emerge and expand. The archaeological record suggests not catastrophic disruption, but innovation and adaptation. At Sibutu Cave, humans were creating complex adhesives for hafting tools around 72,000 years ago. Remarkably sophisticated technology for supposedly struggling survivors of near extinction. At Pinnacle Point, people were heat-treating stone to improve knapping properties, an advanced technological process requiring considerable skill and knowledge. This behavior continues uninterrupted through the Toba timeframe. These contradictions extend beyond stone tools. If humanity experienced a population crash around 74,000 years ago, we would expect to see evidence in our genetic diversity. While initial studies suggested such a bottleneck, newer research presents a more complex picture. Modern genomic studies have found different patterns in different populations. Some show evidence of expansion during this period. Others show contraction. Others show stability. Not the universal bottleneck we would expect from a global catastrophe. Neanderthal populations, our evolutionary cousins, show no evidence of significant population decline coinciding with Toba. If the eruption created a global volcanic winter severe enough to nearly exterminate Homo sapiens, why didn't it similarly affect Neanderthals? The climate record itself presents contradictions. Marine core samples from Lake Malawi in East Africa show no evidence of the severe cooling predicted by volcanic winter models. The local climate appears to have remained relatively stable through the Toba timeframe. Similarly, cores from the Arabian Sea failed to show the dramatic cooling expected from a decade-long volcanic winter. While some temperature decrease is evident, it appears far less severe than the catastrophic cooling predicted by the traditional Toba theory. Pollen records from various sites show less disruption to plant communities than would be expected during a prolonged volcanic winter. While some regions show vegetational changes, others demonstrate remarkable stability through the Toba timeframe. These contradictions have forced researchers to reconsider fundamental assumptions about Toba's impact. Was the eruption less climatically significant than previously believed? Did it affect different regions in dramatically different ways? Or have we misinterpreted the evidence entirely? The conventional narrative assumes Toba ejected massive amounts of sulfur dioxide into the stratosphere, creating a global aerosol veil that blocked sunlight and cooled the planet. But recent chemical analyses of Toba deposits suggest lower sulfur content than initially estimated. If Toba ejected less sulfur than previously thought, its climatic impact would have been less severe and shorter-lived. This could explain why archaeological and paleoclimate records show less disruption than the catastrophic theory predicts. Another contradiction emerges when we examine human migration patterns. If Toba caused near extinction, we would expect evidence of a population crash followed by expansion from a single region, most likely Africa, where the majority of humans lived. Instead, we find evidence of multiple human populations in different regions before, during, and after the Toba timeframe. The genetic pattern suggests not a single bottleneck and expansion, but a complex mosaic of regional population changes. These contradictions raise profound questions about what actually happened 74,000 years ago. If not Toba-induced catastrophe, what explains the genetic pattern suggesting population reduction? If some human groups thrived while others declined, what factors determined survival? As we search for answers, we must consider alternative explanations. Perhaps Toba's impact varied dramatically by region, devastating some areas while leaving others relatively unscathed. Perhaps human cultural adaptations provided better buffers against environmental stress than previously thought. Or perhaps we've been focusing on the wrong event entirely. What if the population dynamics we observed during this period resulted not primarily from Toba, but from competition between different human species, changes in resource distribution, or other environmental factors? The mystery deepens when we consider recent dating of the Toba eruption itself. While traditionally placed at approximately 74,000 years ago, newer techniques have suggested dates ranging from 73,000 to 75,500 years ago, creating uncertainty about exactly when the eruption occurred. This dating uncertainty makes it difficult to correlate the eruption precisely with climate records and archaeological evidence. Events once thought to coincide exactly with Toba might actually precede or follow it, further complicating our understanding of cause and effect. Even more perplexing, recent studies of ancient soils suggest that parts of Africa may have been experiencing significant drought conditions before Toba erupted. These climate stresses could have affected human populations independently of any volcanic effects. If drought was already challenging human populations in Africa, Toba's eruption might have compounded existing pressures rather than creating them. The population dynamics we observe might reflect this complex interaction of multiple environmental stressors. The contradictions extend to human behavior. If our species experienced a catastrophic bottleneck around 74,000 years ago, we would expect evidence of dramatic behavioral changes, desperate survival strategies, technological simplification, abandonment of symbolic activities. Instead, the archaeological record shows the opposite pattern. Complex behaviors increase after this time period. Symbolic expression becomes more common. Technologies grow more sophisticated. These patterns suggest not desperate survival, but cultural flourishing. For example, the oldest known deliberately engraved patterns, geometric markings on ochre pieces from Blombos Cave in South Africa, date to approximately 73,000 years ago, right after Toba's eruption. This is symbolic behavior, not the desperate activity of near-extinction survivors. Similarly, shell beads used for personal adornment, clear evidence of symbolic thinking, appear in increasing numbers after the Toba timeframe. This suggests populations with cognitive capacities and social structures complex enough to support non-utilitarian activities. As our investigation continues, the contradictions multiply rather than resolve. The conventional narrative of Toba-induced catastrophe, while elegant and compelling, struggles to accommodate the growing body of archaeological, genetic, and paleoclimate evidence. So what really happened 74,000 years ago? To answer this question, we must broaden our investigation beyond the physical evidence of Toba's eruption. Perhaps clues lie in unexpected places, in myths and legends, in anomalous discoveries, in patterns we've overlooked. In our next chapter, we'll explore these alternative sources of evidence. We'll examine whether ancient myths might preserve memories of volcanic catastrophe. We'll consider anomalous findings that don't fit neatly into current theories. We'll look for patterns across disciplines. The mystery of what happened 74,000 years ago remains unsolved. But as contradictions in the conventional narrative multiply, we draw closer to a more complex and perhaps more interesting truth about our species' closest brush with extinction. Chapter 6. Echoes in Myth and Memory. Could echoes of what happened 74,000 years ago still resonate in human cultural memory? While no written records exist from this distant era, some researchers suggest that catastrophic events might leave impressions so profound they persist in oral traditions across millennia. This may seem far-fetched. How could stories survive tens of thousands of years? Yet studies of Australian Aboriginal oral traditions have documented accurate descriptions of coastal flooding events that occurred 7,000 to 10,000 years ago as sea levels rose after the last ice age. If memories of geographic changes can persist for 10,000 years, might memories of a volcanic catastrophe as dramatic as Toba persist even longer? Encoded in myths, legends, and religious narratives passed down through countless generations. Flood myths present an intriguing possibility. Nearly every culture on Earth possesses legends of a great flood that destroyed most of humanity, leaving only a few survivors to repopulate the world. Could these widespread narratives preserve distant memories of Toba's aftermath? While flood myths are typically interpreted as reflecting more recent events, local floods or the end of the last ice age, their near universality and similar structure across cultures raises questions. Why do so many human societies tell essentially the same story? Volcanic imagery appears in numerous mythological traditions. Stories of fire from the sky, darkness at noon, ash falling like snow, and years without summer appear in folklore worldwide. These narratives mirror the expected effects of a supervolcanic eruption. Hindu mythology contains the concept of pralaya, periodic dissolutions of the world followed by recreation. One form, Namitika pralaya, describes cosmic dissolution through fire. Could such myths preserve cultural memories of catastrophic volcanic events like Toba? In Norse mythology, Ragnarok describes a series of disasters, including the Fimbulwinter, 3 successive winters without summer between them, followed by the world's submersion in water. This eerily parallels the expected sequence of volcanic winter, followed by flooding from melting ice. The biblical accounts in Genesis describe a time when all the fountains of the great deep burst forth, and the windows of the heavens were opened. While traditionally interpreted as a flood narrative, this imagery also resembles descriptions of explosive volcanic eruptions. Indigenous mythologies from regions near Toba contain numerous stories of fire mountains, sky darkness, and subsequent floods. These narratives, while impossible to date precisely, suggest that memories of volcanic catastrophes persisted in oral traditions for remarkable periods. The Batak people, who live around Lake Toba today, maintain traditions about a primordial catastrophe involving fire, darkness, and flooding. While these myths likely incorporate elements from more recent eruptions, they may preserve core memories of ancient events. Chinese folklore includes accounts of the time of 10 suns, when the world nearly burned, followed by years of darkness and cold. Japanese mythology describes the sun goddess Amaterasu hiding in a cave, plunging the world into darkness until she was coaxed out. These mythic patterns, catastrophe, darkness, cold, near extinction, and renewal, appear with remarkable consistency across cultures separated by vast distances. Could they represent the cultural imprint of Toba, transformed through millennia of oral transmission? Of course, we must approach such interpretations cautiously. Human societies create origin myths for many reasons. Similar stories could emerge independently from universal human experiences with local disasters, without necessarily preserving memories of Toba specifically. But the pattern is suggestive enough to consider alongside physical evidence. If Toba's eruption was as catastrophic as traditional theory suggests, it would have been the most dramatic event witnessed by humans to that point, potentially leaving psychological scars across generations. Moving beyond myth to physical evidence, we find anomalies that challenge conventional narratives. In India, stone tools discovered above the Toba ash layer show technological continuity with those below, contradicting expectations of population crash and cultural disruption. More puzzling still are findings from Malaysia's Lenggong Valley, where hand axes found above and below the Toba ash layer show remarkable consistency in craftsmanship. These tools, dated to approximately 70,000 years ago, suggest skilled human presence despite proximity to Toba. In Africa, archaeological sites show evidence of increasing behavioral complexity immediately after the Toba timeframe, precisely when humans supposedly teetered on extinction. This includes the first definitive evidence of symbolic behavior, such as engraved patterns on ochre. At Pinnacle Point in South Africa, humans were harvesting shellfish and using fire to improve stone tool materials around 71,000 years ago. Sophisticated behaviors emerging shortly after Toba. This suggests thriving populations, not desperate survivors of catastrophe. Perhaps the most striking anomaly appears in genetic studies of Neanderthals and Denisovans, our evolutionary cousins. Neither species shows clear evidence of population crash coinciding with Toba. Strange if the eruption created a global volcanic winter. If Toba nearly exterminated Homo sapiens, why didn't it similarly affect other human species? Neanderthals and Denisovans occupied more northern latitudes that should have experienced even more severe volcanic winter effects than tropical human populations. Another anomaly. Different human populations show different genetic patterns during this time frame. Some appear to contract, others expand, others remain stable. This complex mosaic contradicts expectations of a single global bottleneck affecting all populations similarly. Marine sediment cores from some regions show limited evidence of the dramatic cooling predicted by volcanic winter models. While some cooling occurred, its magnitude and duration appear insufficient to trigger the catastrophic ecosystem collapse envisioned by traditional Toba theory. Even more puzzling, archaeological evidence suggests humans were expanding their range during and immediately after the Toba timeframe. Sites in Australia dated to approximately 65,000 years ago indicate humans successfully navigated open water to reach the continent. This successful colonization of new territories seems inconsistent with a species recovering from near extinction. It suggests populations with the numbers, resources, and technological capacity to undertake risky voyages to unknown lands. The distribution of mitochondrial DNA, haplogroups, genetic lineages passed exclusively from mother to child, shows patterns difficult to reconcile with a severe bottleneck around 74,000 years ago. Some lineages appear to have diverged before this time frame and survived. While genetic evidence does suggest population reductions during our species' history, the timing and severity of these bottlenecks remain contested. Some may have occurred earlier, around 150,000 years ago, or later than the Toba eruption. One possibility is that multiple population bottlenecks occurred at different times in different regions, creating a more complex pattern than the single, Toba-induced near-extinction event proposed by traditional theory. Another anomaly appears in climate records. If Toba triggered a decade-long volcanic winter, we would expect clear evidence in ice cores from Greenland and Antarctica. While some cores show sulfate spikes potentially linked to Toba, their magnitude suggests more moderate climate effects. The most significant anomaly may be the emerging evidence that Toba contained less climate-altering sulfur than previously believed. Chemical analysis of Toba glass suggests the eruption may have ejected less sulfur dioxide into the stratosphere than earlier estimates indicated. Without massive sulfur emissions, Toba's climate impact would have been primarily regional rather than global. potentially explaining why archaeological and paleoclimate records show less disruption than catastrophic models predict. These anomalies don't disprove Toba's significance in human evolution. Rather, they suggest a more complex story, one where Toba played a role alongside other factors including changing climates, competition between human species, and cultural adaptations that buffered environmental stresses. As we continue our investigation, a new possibility emerges. What if Toba's primary impact wasn't killing humans directly through volcanic winter, but rather accelerating evolutionary processes already underway? What if it was a catalyst rather than a catastrophe? Chapter 7. The Evolutionary Crucible. As we reconsider what happened 74,000 years ago, the stakes of our investigation grow. Understanding this critical period isn't merely about correcting the historical record. It's about comprehending the forces that shaped human evolution at a pivotal moment. Forces that made us who we are. If Toba didn't cause near extinction through volcanic winter, what explains the genetic and archaeological patterns we observe? A new, more complex narrative is emerging, one where Toba acted not as a single catastrophic event, but as an accelerant of evolutionary processes already underway. This period, roughly 80,000 to 60,000 years ago, coincides with remarkable changes in human behavior and capabilities. We see the first consistent evidence of symbolic thinking. Complex technologies emerge. Long-distance trade networks develop. Art appears. These developments, collectively termed behavioral modernity, have traditionally been explained as either gradual evolution or sudden cognitive change. But what if environmental stress, including but not limited to Toba, played a crucial role in accelerating these changes? The stakes of this question extend beyond academic debate. If environmental catastrophe spurred human innovation rather than nearly ending our species, it transforms our understanding of human resilience and adaptability in the face of existential threats. This alternative narrative suggests humans not only survived Toba and other environmental challenges, but may have evolved new capabilities in response to them. Stress-induced innovation rather than near extinction and lucky survival. Consider the archaeological evidence again. After the Toba timeframe, we see increasing sophistication in stone tool technologies across Africa and Eurasia. The Middle Stone Age transitions toward more complex Upper Paleolithic toolkits with greater specialization. We observe the first definitive evidence of symbolic representation, including the engraved ochre pieces at Blombos Cave, dated to approximately 73,000 years ago. Abstract thinking, once sporadic, becomes more consistent in the archaeological record. Shell beads used for personal adornment appear in increasing numbers. These items serve no direct survival function. They represent symbolic communication, possibly indicating social status, group identity, or other abstract concepts. Long-distance trade networks develop, with materials transported hundreds of kilometers from their sources. This suggests not only mobility, but social connections spanning multiple human groups, the beginnings of wider cultural exchange. These developments represent more than technological advancement. They signify cognitive changes, new ways of thinking about the world, new forms of social organization, new methods of storing and transmitting knowledge across generations. The traditional Toba catastrophe theory struggles to explain this pattern. If humans were reduced to a few thousand individuals fighting for survival, we would expect technological simplification and focus on immediate survival needs, not flourishing symbolic expression and social complexity. But what if environmental stress, including Toba's eruption, actually selected for greater cognitive flexibility, social cooperation, and innovative thinking? What if those who survived and thrived were precisely those with enhanced capabilities for adaptation? This alternative narrative transforms our understanding of human evolution during this critical period. Rather than a story of near extinction and lucky survival, it becomes a story of adaptation, innovation, and evolutionary pressure selecting for distinctly human capabilities. The stakes escalate further when we consider what this means for understanding modern human origins. If Toba and other environmental stressors accelerated human cognitive evolution, they helped create the behavioral modernity that defines our species. This perspective shifts Toba from near destroyer of humanity to unintentional architect of human uniqueness. The very qualities that define us as modern humans, our symbolic thinking, technological innovation, and complex social structures, may have been forged in environmental crisis. Evidence for this alternative narrative comes from multiple sources. Genetic studies increasingly suggest that different human populations experienced different demographic histories during this period, some contracting, others expanding, others remaining relatively stable. This complex mosaic of population changes aligns better with regionally variable environmental impacts than with a single global catastrophe. Some populations may have declined due to local conditions while others thrived, creating opportunities for cultural exchange and technological diffusion. Archaeological evidence shows that sophisticated technologies appear first in some regions, then spread to others, suggesting innovation happened in multiple centers rather than emerging from a single bottleneck population. The timing of human dispersal out of Africa becomes critical evidence. If humans were reduced to a few thousand individuals around 74,000 years ago, we would expect a significant delay before populations recovered enough to expand their range. Instead, archaeological evidence suggests humans were successfully colonizing new territories shortly after the Toba timeframe. Sites in Australia dated to approximately 65,000 years ago indicate humans had not only recovered, but were thriving enough to undertake challenging sea voyages. This pattern suggests not catastrophic decline, but continued adaptation and expansion, potentially accelerated rather than hindered by environmental challenges, including Toba's eruption. The stakes of our investigation grow even larger when we consider implications for modern challenges. If human innovation accelerated during periods of environmental stress, what does this suggest about our capacity to adapt to current threats like climate change? Does our evolutionary history suggest inherent resilience in the face of environmental catastrophe? Or does it indicate that innovation emerges specifically from stress, suggesting that comfort might actually slow rather than enhance our adaptive capabilities? These questions aren't merely philosophical. They strike at the heart of how we understand human nature and our relationship with environmental change. Was crisis essential to making us human? Does challenge drive our most significant innovations? The evidence increasingly suggests that Toba was not an isolated event but part of a complex period of environmental fluctuation that included changing climates, shifting resource distributions, and competition between different human species. This period of environmental flux may have created precisely the conditions needed to select for enhanced cognitive flexibility, technological innovation, and social cooperation, the defining characteristics of behavioral modernity. As different human populations faced varying challenges, those with greater capacity for innovation and adaptation would have thrived. Those who could communicate abstract concepts, maintain larger social networks, and develop new technologies would have enjoyed selective advantages. This selection pressure may have been particularly intense for populations living at the edges of habitable zones, areas where environmental stress was greatest and adaptation most necessary for survival. The archaeological record supports this pattern. Some of the earliest evidence for complex symbolic behavior appears in South Africa, a region at the southern edge of human habitation during this period, where environmental fluctuations would have created significant adaptive challenges. Similarly, evidence for advanced technologies and symbolic expression appears early in regions where different human species overlapped, areas where competition and cultural exchange might have accelerated innovation. As our investigation deepens, a new narrative emerges, What if Toba's eruption was not the cause of human population dynamics during this period, but rather an accelerant of processes already underway? What if it intensified selection pressures that were already shaping human evolution? This alternative narrative transforms how we understand our species' closest brush with extinction. Perhaps we weren't simply lucky survivors of catastrophe, but active adapters whose distinctly human capabilities emerged precisely because of environmental challenges. The traditional Toba catastrophe theory presents a dramatic story of near extinction and recovery. But the emerging alternative narrative may be even more profound, a story of crisis driving innovation, of environmental stress selecting for the very qualities that make us human. As we prepare to enter the final phase of our investigation, the stakes have never been higher. We're not simply questioning when and how a supervolcano erupted 74,000 years ago. We're reconsidering the forces that shaped human evolution at a critical juncture. We're re-examining what it means to be human. If our distinctive capabilities emerged not despite, but because of environmental challenges, it transforms our understanding of human nature and our relationship with planetary change. In our next segment, we'll explore the most recent scientific evidence about what really happened 74,000 years ago. We'll examine cutting-edge genetic studies, new archaeological discoveries, and refined climate models that are reshaping our understanding of this pivotal moment. We'll consider whether human evolution follows a pattern of punctuated equilibrium, long periods of relative stability interrupted by rapid change during times of environmental stress. And we'll ask whether Toba's eruption might represent one such punctuation point. The mystery deepens and the implications grow more profound. What really happened 74,000 years ago may reveal not just the story of our species' survival, but the very origins of what makes us uniquely human. Chapter 8. 3 Paths to Understanding. As we approach the climax of our investigation, 3 compelling theories emerge to explain what really happened 74,000 years ago. Each provides a distinct lens through which to view this pivotal moment in human evolution, and each carries profound implications for understanding our species' journey. The first theory, which we might call the traditional catastrophe model, maintains that Toba's eruption triggered a severe volcanic winter that nearly exterminated humanity. In this view, a few thousand survivors, primarily in Africa, eventually repopulated the planet. This theory draws support from early genetic studies suggesting a population bottleneck, climate models predicting severe cooling effects from Toba's eruption, and the timing coincidence between Toba and apparent changes in human population dynamics and behavior. Proponents argue that surviving such a catastrophe would have created intense selection pressure, favoring those with the greatest cognitive flexibility, social cooperation, and technological innovation, potentially explaining the emergence of behavioral modernity shortly afterward. In this view, modern humans represent the descendants of catastrophe survivors whose adaptability allowed them to endure conditions that drove other populations to extinction. Our current global dominance stems directly from capabilities forged in this evolutionary crucible. The second theory, which we might call the regional impact model, suggests Toba's effects vary dramatically by geography. Some populations experienced severe disruption, while others remained relatively unaffected, creating a complex mosaic of regional population dynamics. This theory is supported by archaeological evidence showing continuity in some regions, but disruption in others. Genetic studies revealing different demographic histories for different populations, and climate data suggesting regionally variable impacts rather than uniform global cooling. Proponents argue that this regional variability created natural experiments in human adaptation, with different populations developing different solutions to environmental challenges. Subsequent cultural exchange between these groups accelerated innovation as adaptive strategies spread. In this view, modern humans represent the product of multiple population histories that occasionally intersected, separated, and reconnected, creating a complex evolutionary tapestry rather than a single line of descent from catastrophe survivors. The regional impact model better explains archaeological evidence showing technological continuity in some regions like India and South Africa, while accounting for apparent population reductions in other areas such as parts of Europe and Central Asia. The third theory, which we might call the catalyst model, suggests Toba was not the primary cause of human population dynamics during this period, but rather one factor among many, including changing climates, competition between human species, and internal cultural developments. This theory is supported by evidence that significant environmental fluctuations were already occurring before Toba erupted, that human behavioral innovations were already emerging, and that Toba's climate impacts may have been less severe than initially modeled. Proponents argue that Toba accelerated processes already underway, intensifying selection pressures, disrupting established patterns, and creating opportunities for innovative adaptations to spread. The eruption was a catalyst rather than a primary cause of evolutionary change. In this view, modern humans represent the product of cumulative adaptations to multiple environmental challenges over time, with Toba representing one particularly dramatic challenge among many that shaped our species' evolution. The catalyst model explains why behavioral modernity emerges gradually rather than suddenly after Toba, with innovations appearing at different times in different regions, rather than radiating from a single source population of catastrophe survivors. Each of these theories carries different implications for understanding human nature and resilience. The traditional catastrophe model suggests we are descendants of exceptional survivors whose adaptability allowed them to endure near extinction. The regional impact model suggests we are products of diverse evolutionary histories that occasionally converged and diverged, with different populations developing different adaptive strategies that eventually combine through cultural exchange. The catalyst model suggests we are the result of cumulative adaptations to ongoing environmental fluctuations, with Toba representing one particularly dramatic moment in a longer process of human evolution responding to changing conditions. As we evaluate these competing theories, the evidence increasingly points away from the traditional catastrophe model toward either the regional impact or catalyst models, or perhaps a synthesis of both. Archaeological evidence consistently shows more continuity than would be expected after a near-extinction event. Genetic studies reveal complex population histories difficult to reconcile with a single severe bottleneck. Climate records suggest more moderate cooling than catastrophic models predict. Recent research on Toba itself has revised estimates of its sulfur emissions downward, suggesting its climate impacts were less severe than initially believed. Chemical analysis of Toba glass indicates lower sulfur content than would be needed for decade-long volcanic winter effects. These findings don't diminish Toba's significance. An eruption ejecting 2,800 cubic kilometers of material would have had profound regional impacts and potentially global consequences. But they suggest we need a more nuanced understanding of how those impacts shaped human evolution. The most compelling synthesis suggests Toba had significant but regionally variable effects that interacted with other factors, including climate shifts already underway, competition between different human species, and cultural innovations emerging in various populations. This perspective transforms our understanding of what happened 74,000 years ago. Rather than a single catastrophic near-extinction event, we see a complex interplay of environmental stressors, biological adaptations, and cultural innovations across different human populations. Some groups likely experienced population decline due to Toba's direct effects or the compound impacts of eruption combined with other environmental stresses. Others may have remained relatively stable or even expanded as they adapted to changing conditions. These varying population trajectories created natural experiments in human adaptation, with different groups developing different solutions to environmental challenges. When these populations later reconnected through migration and trade, their innovations could spread and combine. This model better explains the archaeological evidence showing both continuity and change across different regions. It accounts for genetic studies revealing different demographic histories for different populations. It aligns with climate data suggesting regionally variable impacts. Most importantly, it helps explain the emergence of behavioral modernity following this period, not as a sudden development among catastrophe survivors, but as the culmination of adaptations that evolved in different populations facing different challenges. As we prepare to enter the final phase of our investigation, the weight of evidence increasingly supports a more complex narrative than the traditional Toba catastrophe theory. What really happened 74,000 years ago appears to be a story of regional variability, adaptive diversity, and evolutionary catalyst. This revised understanding doesn't diminish the significance of this period in human evolution. If anything, it enhances it, revealing a more nuanced and fascinating story about how our species navigated environmental challenges and emerged with the distinctive capabilities that define us today. In our next segment, we'll examine the newest scientific evidence that has transformed our understanding of this pivotal moment in human evolution. Recent discoveries have upended conventional wisdom and revealed surprising insights about what really happened 74,000 years ago. Chapter 9. The New Science of Human Resilience. The traditional narrative of Toba as humanity's near-extinction event has undergone radical revision in recent years. New scientific techniques, from advanced genetic analysis to precise climate reconstruction, have transformed our understanding of what happened 74,000 years ago. Perhaps the most significant development comes from improved dating methods. Recent research has pinpointed Toba's eruption more precisely to 73,880 years ago, with a margin of error of just 640 years. This precision allows researchers to correlate the eruption with other evidence more accurately. When aligned with this refined chronology, climate records tell a surprising story. Ice cores from Greenland and Antarctica show sulfate spikes consistent with Toba's eruption, but the magnitude suggests more moderate cooling than the catastrophic decade-long winter originally proposed. A 2017 study analyzing marine sediments from Lake Malawi found no evidence of significant cooling in East Africa after Toba. The researchers concluded that the largest known volcanic eruption in the Quaternary did not significantly alter the climate of East Africa. Similarly, the 2018 analysis of paleoclimate records from various sites showed regional variability in climate response. Some areas experienced cooling while others remained relatively stable, contradicting the notion of uniform global volcanic winter. Chemical analysis of Toba glass has revealed lower sulfur content than needed for severe global cooling. While the eruption ejected enormous volumes of ash and rock, it may have released less climate-altering sulfur dioxide than smaller but more sulfur-rich eruptions. These findings present a paradox. How could the largest eruption in 2.5 million years have less climatic impact than expected? The answer appears to lie in the eruption's chemistry, with Toba producing primarily silicic magma relatively poor in sulfur compared to other volcano types. Genetic evidence has undergone similar reassessment. While early studies suggested a severe population bottleneck around Toba's timeframe, more sophisticated analyses using whole genome sequencing rather than just mitochondrial DNA present a more complex picture. A 2018 study examining genetic diversity across multiple human populations found evidence for a series of bottlenecks at different times, rather than a single severe bottleneck coinciding with Toba. Some populations show signals of earlier bottlenecks around 150,000 years ago. Other genetic studies reveal that different human populations experienced different demographic histories during this period, some contracting, others expanding, others remaining stable. This mosaic pattern contradicts expectations of a single global catastrophe affecting all populations similarly. Archaeological evidence increasingly contradicts the catastrophe model. Sites across South Asia show human occupation continuing through the Toba timeframe with technological continuity rather than disruption. Strange if the region experienced severe volcanic winter effects. At sites like Jolapuram in India, sophisticated stone tools appear both below and immediately above the Toba ash layer. The implements show no technological regression or desperate adaptation. That would be expected if populations were struggling for survival under catastrophic conditions. In South Africa, sites like Pinnacle Point and Sibudu caves show continuous human occupation with increasing rather than decreasing technological sophistication through the Toba timeframe. Symbolic behaviors and complex technologies emerge and expand rather than disappear. Perhaps most surprisingly, archaeological evidence indicates humans successfully colonized Australia around 65,000 years ago, just 9,000 years after Toba. This remarkably rapid expansion seems inconsistent with a species recovering from near extinction. These discoveries present another paradox. If Toba didn't cause a global catastrophe, what explains the apparent genetic bottlenecks some studies detect? And what drove the significant behavioral changes that emerge after this period? Recent research suggests multiple factors converged during this critical period. Climate records indicate Toba erupted during a time of already significant climate fluctuation, with rapid shifts between warmer and cooler periods, creating environmental stress independent of volcanic effects. These climate fluctuations would have affected resource distributions, forcing human populations to adapt or migrate. Different regions experience different patterns of change, creating a complex mosaic of environmental challenges rather than a single, uniform catastrophe. Competition between human species intensified during this period. Genetic evidence indicates interbreeding between Homo sapiens, Neanderthals, and Denisovans occurred multiple times, suggesting these populations encountered each other with increasing frequency. These encounters likely involved both competition and cultural exchange, creating selection pressure for innovation while simultaneously facilitating the spread of adaptive technologies and behaviors between different human populations. The emerging picture suggests not a single catastrophe, but a perfect storm of evolutionary pressures, climate fluctuation, volcanic disruption, interspecies competition, and increasing population densities in certain regions, all combining to accelerate human adaptation. This convergence of factors creates a third paradox. How did these challenges lead to innovation rather than extinction? What made humans uniquely capable of turning environmental stress into evolutionary advantage? New research suggests the answer lies in distinctly human capabilities for cultural transmission, social learning, and cumulative innovation. Unlike other species, humans could pass knowledge across generations, allowing adaptations to accumulate rather than being lost when individuals died. This cultural transmission became particularly valuable during periods of environmental stress, when the ability to preserve and share knowledge about survival strategies could mean the difference between extinction and adaptation. Studies of modern hunter-gatherer groups demonstrate how cultural knowledge buffers environmental variability with sophisticated understanding of plants, animals, weather patterns, and geography, allowing adaptation to changing conditions without requiring genetic change. During the Toba timeframe, this capacity for cultural adaptation may have reached a critical threshold, with sufficiently complex communication systems allowing the preservation and transmission of increasingly sophisticated knowledge across generations and between groups. Archaeological evidence supports this theory, showing rapid diversification of tool technologies and symbolic expression after Toba. These developments represent not just new tools, but new systems for preserving and communicating knowledge. The engraved ochre pieces from Blombos Cave, dated to approximately 73,000 years ago, demonstrate symbolic notation, potentially representing an early system for storing information outside human memory. a critical development for cumulative cultural evolution. Shell beads and other personal ornaments, appearing with increasing frequency after Toba, may have served as markers of group identity and status, facilitating more complex social organizations that could coordinate larger-scale cooperative activities. These innovations created positive feedback loops. More effective knowledge transmission allowed better adaptation to environmental challenges. Better adaptation supported larger, more connected populations. Larger populations created more opportunities for innovation. The newest scientific evidence thus reveals not a story of catastrophe and lucky survival, but something more remarkable, a story of how environmental challenges accelerated the very adaptations that make humans unique among Earth species. As we approach the culmination of our investigation, the paradoxes multiply rather than resolve. If not near extinction by volcanic winter, what really happened 74,000 years ago? And why did this period prove so transformative for human evolution? The answers to these questions will reshape our understanding not just of a single event in prehistory, but of the very forces that made us human. In our final segment, we'll synthesize the evidence to reveal what really happened 74,000 years ago and why it matters for understanding our future. Chapter 10: The Adaptive Revolution. As we reach the climax of our investigation, the evidence converges toward a remarkable conclusion. What really happened 74,000 years ago wasn't a single catastrophic event that nearly ended humanity, but rather a perfect storm of evolutionary pressures that fundamentally transformed our species. Toba's eruption, while enormous, appears to have been just one factor among many. It created significant but regionally variable impacts, interacting with climate fluctuations already underway, changing resource distributions, and increasing competition between different human populations. This convergence of challenges created unprecedented selective pressure for adaptation. But unlike previous evolutionary bottlenecks in Earth's history, something extraordinary happened. Humans responded not primarily through genetic change, but through cultural innovation. This represents the true revelation of our investigation. 74,000 years ago marked not humanity's near extinction, but the tipping point of a fundamental transformation in how our species adapts to environmental change, what we might call the adaptive revolution. Before this period, human adaptation occurred primarily through the same mechanisms as other species, genetic changes accumulating over many generations, slowly altering physical characteristics and instinctual behaviors in response to environmental pressures. But during the critical period around Toba, archaeological evidence shows humans increasingly relied on cultural adaptation, developing new technologies, social organizations, and knowledge systems that could respond to environmental challenges within a single generation. This shift from primarily genetic to primarily cultural adaptation represents one of the most significant transformations in the history of life on Earth. It fundamentally changed the relationship between humans and their environment, accelerating our adaptive capacity by orders of magnitude. Cultural adaptation allowed humans to respond to environmental changes in years or decades, rather than thousands of generations. New tools, techniques, and knowledge could spread through social learning without requiring genetic changes to become established in populations. The evidence for this adaptive revolution appears throughout the archaeological record. Stone tool technologies diversify rapidly after Toba. Novel hunting strategies emerge. The first definitive evidence of symbolic expression and abstract thinking appears. These innovations represent more than new technologies. They demonstrate new ways of preserving and transmitting knowledge, the foundations of cumulative cultural evolution that would eventually lead to writing, mathematics, science, and civilization itself. This adaptive revolution explains many patterns that the traditional catastrophe theory struggled to account for. It explains why we see increasing rather than decreasing behavioral complexity after Toba, It explains regional variations in human populations and technologies. It explains how humans could expand into challenging new environments like Australia shortly after Toba. Cultural adaptation allowed our ancestors to develop specialized technologies and knowledge systems for exploiting resources in previously uninhabitable regions. This revelation transforms our understanding of what makes humans unique among Earth species. Our defining characteristic isn't a particular physical trait or cognitive capacity, but our unprecedented ability to adapt through culture rather than biology. This ability emerged gradually, but the period around Toba appears to represent a critical threshold when the complexity of human cultural transmission reached a level that allowed truly cumulative innovation, creating positive feedback loops of increasing adaptive capacity. The traditional Toba catastrophe theory got one thing right. This period was indeed pivotal in human evolution, but it wasn't because we nearly went extinct. It was because environmental challenges accelerated the very adaptations that would eventually make us the planet's dominant species. This understanding resolves many of the paradoxes we've encountered in our investigation. It explains why different human populations show different genetic histories during this period. They experience different challenges and develop different adaptive strategies. It explains why we see technological continuity in some regions, but innovation in others. Cultural adaptation responded to local conditions rather than following a single trajectory. It explains the apparent contradiction between population continuity and behavioral change. Most significantly, it explains why distinctly human behaviors, symbolic expression, complex technology, long-distance trade networks proliferate after this period. These weren't desperate adaptations of near-extinction survivors, but sophisticated cultural solutions to environmental challenges. Recent genetic evidence supports this narrative. Studies of genes involved in brain development and social cognition show signatures of positive selection during this period, suggesting environmental pressures were favoring enhanced capabilities for cultural learning and social cooperation. Neurological adaptations that facilitated more complex language, better social learning, and enhanced working memory would have created significant advantages for individuals, navigating rapidly changing environmental conditions through cultural rather than genetic adaptation. The timing coincides with archaeological evidence for increasingly sophisticated symbolic expression and social coordination. The first definitive evidence of abstract notation, the engraved patterns on ochre from Blombos Cave, dates to approximately 73,000 years ago. Shell beads used for personal adornment appear with increasing frequency after Toba. These weren't merely decorative but served social functions, potentially marking group identity, status, or relationships that facilitated more complex social organizations. These innovations created new possibilities for human adaptation. Better symbolic communication allowed more effective knowledge transmission across generations. More complex social organizations facilitated larger-scale cooperative activities. Cumulative innovation accelerated. The big reveal of our investigation thus contradicts the traditional narrative in a profound way. What happened 74,000 years ago wasn't a catastrophe that nearly ended humanity. It was a crucible that forged humanity as we know it today. Toba's eruption, combined with other environmental challenges of this period, didn't merely destroy our species. It helped create the conditions that transformed us from just another hominin species into the uniquely adaptive beings who would eventually develop global civilization. This transformation wasn't a dramatic overnight change, but it represented a critical threshold when human cultural adaptation reached a level of sophistication that allowed it to become the primary mechanism through which our species responds to environmental challenges. The implications of this revelation extend far beyond understanding our past. They speak directly to current challenges like climate change, pandemic disease, and other global threats. Our species' greatest strength isn't any particular technology, but our unprecedented adaptive capacity. Throughout human history, our most significant innovations have often emerged during periods of environmental stress, not despite challenges, but because of them. Crisis has repeatedly spurred creativity, forcing the development of novel solutions that transform our relationship with the world. This pattern suggests something profound about human nature and our future prospects. We are not simply victims of environmental change, but active adapters whose greatest innovations often emerge precisely when conditions force us beyond comfortable established patterns. The evidence from 74,000 years ago reveals that humans possess remarkable resilience, not because we're physically hardy. We're actually quite fragile compared to many species, but because our cultural adaptive systems allow us to transform challenges into opportunities for innovation. This doesn't mean environmental catastrophes are desirable. They invariably cause suffering and disruption. But it suggests that if we understand and leverage our unique adaptive capabilities, we can navigate even extreme challenges while developing transformative solutions. The story of what really happened 74,000 years ago thus offers something more valuable than the traditional catastrophe narrative, not just a tale of lucky survival, but insights into the very processes that make human adaptation so extraordinary. As we face current and future environmental challenges, this understanding becomes not just academically interesting, but potentially crucial for our continued success as a species. The lesson from 74,000 years ago isn't that we got lucky once, but that crisis itself can drive transformation. This doesn't guarantee success in facing current challenges like climate change. Cultural adaptation still requires time, resources, and favorable conditions. But it suggests we possess capacities for transformation that go far beyond what most other species can achieve. The true story of what happened 74,000 years ago isn't a dramatic near-miss with extinction, but something even more remarkable: the emergence of humanity's defining characteristic, our unprecedented capacity for cultural adaptation that would eventually transform the planet itself. As our journey into humanity's most consequential moment concludes, we return to the beach where we began, standing under ash-darkened skies 74,000 years ago. But we see this scene differently now, not as the near end of our story, but as its transformation. The human figures moving across this landscape weren't merely lucky survivors clinging to existence. They were active adapters developing new technologies, new social organizations, new ways of understanding and responding to their changing world, innovations that would reshape human evolution. What happened 74,000 years ago wasn't a bottleneck that nearly ended humanity, but a crucible that transformed it, accelerating the shift from biological to cultural adaptation that defines our species and ultimately led to the development of global civilization. This understanding carries profound implications. If environmental challenges drove our most significant evolutionary adaptations, what does this suggest about our current moment as we face unprecedented global threats from climate change, resource depletion, and other anthropogenic crises? Perhaps these challenges, while undeniably dangerous, also create conditions for transformation, forcing innovations that might otherwise never emerge. Perhaps crisis itself serves as catalyst for human creativity, pushing us beyond comfortable patterns toward revolutionary solutions. This doesn't mean we should welcome catastrophe. The suffering and disruption that environmental crises cause are very real. But it suggests that if we understand and harness our unique adaptive capacities, we may navigate even extreme challenges while developing transformative responses. The lessons from 74,000 years ago offer something more valuable than a dramatic story of near extinction. They reveal the very processes that make human adaptation extraordinary, our ability to respond to environmental challenges through cultural innovation rather than awaiting genetic change. As we close our investigation, the mystery of what happened 74,000 years ago transforms from a question about human survival to a revelation about human becoming. How environmental challenges helped forge the very qualities that make us uniquely human. Perhaps this is our species' defining paradox, that our greatest strengths emerge not despite environmental challenges, but because of them. Crisis, serving as the catalyst for creativity. Adversity, accelerating adaptation. Not mere endurance, but transformation through challenge. If you found this journey into humanity's defining moment illuminating, subscribe for more explorations of the mysteries that shaped our existence. Until next time, remember that understanding our past may be the key to navigating our future, a future where, as always, adaptation will determine survival.